In section 3, we're going to take a look at the graphs of our other trig functions. So although we're not going to see these graphs as often, they can be transformed as well. So we're going to first look at our tangent function. So the special thing about tangent function, its domain is different than sine and cosine. And if we're thinking about applying this to the unit circle, for the tangent function, we can't divide by 0. And with the tangent function on the unit circle, we would divide by 0 when cosine is 0. And this happens 2 places on the unit circle, at pi over 2 and at 3 pi over 2. So if we look at the graph of tangent of x, we can see that pi over 2 and 3 pi over 2 are excluded. They are asymptotes for our tangent function. So we can go ahead and generalize information about the tangent function. So first of all, its domain is going to be all real numbers except pi over 2 plus k pi, where k is an integer. So if you can look at the graph, every time we travel a distance of pi, we have our graph is stopped. So unlike our previous sine and cosine functions where the range was strictly between -1 and 1, the range for a tangent function, as you can see from the graph, is all real numbers, so -infinity to infinity. There is no restriction on the range for tangent. Next, we want to look at the period. So for sine and cosine, the period was 2 pi. But if we look at our graph here, the tangent function fits between -pi over 2 and pi over 2, which only has a period of pi. So the period of our tangent function is pi. That then leads us into our asymptotes. So if we look at the graph, I can draw lines through between -pi over 2, pi over 2, 3 pi over 2. So those values that we exclude from the domain, I can draw asymptotes there, and my graph of tangent is stuck between those asymptotes. So for our asymptotes, those appear when x equals pi over 2 plus k pi, where again, k is an integer. And lastly, our x-intercepts. So if we're looking at our graph, our x-intercepts are at 0, pi, and 2 pi, and we can go to -pi and -2 pi. So our x-intercepts occur every multiple of pi. So we can write those as x equals k pi, where again, k is an integer. Next, let's take a look at the cotangent function. So similar to the tangent function, the domain of the cotangent function, we can't divide by 0. And for the cotangent function, because it's the reciprocal of tangent, we can't divide by 0 on the unit circle when sine is 0, which happens at pi and 2 pi. Which you can see in our graph here is that we have no graph at those x values. So if we go into the generalizing using our graph of cotangent, it looks very similar to the tangent function, except the graph goes the curved portions of our graph go the opposite direction, and it has different asymptotes. So first we start with the domain. So we're going to have all real numbers except this time we're going to exclude the multiples of pi, going by values of pi as well. So just k pi, again, where k is an integer. Its range is going to be all real numbers because there's no excluded possible values I can get out for cotangent. Its period is, because it's the reciprocal of tangent, it's going to have the same period of tangent as well. So its period is also going to be pi. And again, you can look at the graph. If I look between 0 and pi, I get one curved portion of our graph. So then we look at the asymptotes. So I can draw, if I draw my asymptotes, they happen at pi, 2 pi, 0, negative pi, and negative 2 pi. So my asymptotes we can write as x equals k pi, where again k is an integer. And lastly, our x-intercepts. So we look at the graph, our x-intercepts are pi over 2, 3 pi over 2, negative pi over 2, and negative 3 pi over 2. So its x-intercepts are going to be at x equals pi over 2 plus k pi, where k is an integer. So if we're comparing the cotangent and tangent graphs, their values excluded from the domain and x-intercepts are just switched, which makes sense because they are reciprocals of each other. It does make sense that the domain, asymptotes, and x-intercepts would be switched as well. Now let's move on to our reciprocals for sine and cosine. So we're going to start with the cosecant function. And similar to when we were doing the tangent and cotangent functions, cosecant functions, we also can't divide by 0. So because cosecant is the reciprocal of sine, we can't divide by 0 when the y value is 0. So that would happen at pi and 2 pi, which is similar to the domain of cotangent. So the domain for cosecant is going to be the same. We're going to have all real numbers except k pi, where again k is an integer. Its range, if we look at the graph for cosecant, I don't actually have any y values between -1 and 1. So our range is only going to be from -infinity to -1, union 1 to infinity. And this comes from the domain of sine being between -1 and 1, so its range for its reciprocal is going to be outside of that. That leads us into the period. Because it is the reciprocal of sine, the period for cosecant is going to also be 2 pi. As we can see from the graph, it also has asymptotes. We draw them. They appear at multiples of pi, so they're going to be at x equals k pi, where again k is an integer. And lastly, we look at the x-intercepts. And if we look at the graph of cosecant, we can actually see that the graph never crosses the x-axis, so we're not going to have any. So we're going to put none. Lastly, we look at the graph of the secant function. So again, very similar to all our other functions, for the domain of the secant function, we can't divide by 0. And because secant is the reciprocal of cosine, we want to know when x is 0. And that happens at pi over 2 and 3 pi over 2 on the unit circle. So that's why you can see on our graph here, the function never lands on those values. So we have our graph of secant of x. So its domain is going to be all real numbers except pi over 2 plus k pi, where again k is an integer. its range, similar to the cosecant function, we don't have any y values between -1 and 1, so its range is from -infinity to -1, and then from 1 to infinity. And again, this comes from the fact that the cosine function is between -1 and 1, so when I do the reciprocal, it's going to be outside of that. Now for the period, because again it is the reciprocal of cosine, it has the same period, which is 2 pi. Its asymptotes, if we look at our graph, if we draw our asymptotes, they appear at every pi away from our pi over 2 values. So we have x equals pi over 2 plus k pi, where again k is an integer. And lastly, our x-intercepts. Again, if you look at the graph, our function never crosses the x-axis, so it doesn't have any x-intercepts. Let's go ahead and do some examples where we graph some of these trig functions. So unlike our sine and cosine functions where we had to create a table of values based on the period and phase shift, for our other trig functions, we only care about the period and the asymptotes. Because the graph looks the same between those asymptotes, either a curve or a parabola, we only need to know the period and the location of our asymptote. So if we start at, for the example, f of x equals 2 tangent of 2x. The way we find the period doesn't change between sine and cosine. But because the general period for tangent is pi, instead of doing 2 pi over b, we're going to do pi over b. And in this example, that would be pi over 2. So we know that our function is going to be between pi over 2. So for the location of our asymptotes, because we have split our period in half, the location of our asymptotes is also going to be in half as well. So instead of being at pi over 2 and multiples of pi after that, we're actually going to be at x equals half of pi over 2 is pi over 4. And instead of multiples of pi, we'll be in multiples of pi over 2. So we want to graph our asymptotes first. So pi over 4 and negative pi over 4. And then the distance between negative pi over 4 and pi over 4 is pi. So then if I just graph my tangent function between those, and this is one period of our function f of x equals 2 tangent of 2x. And we want to repeat this pattern, and our asymptotes are going to appear every distance of pi over 2 from pi over 4. So our next asymptote and then our graph is going to fall in between. And this is going to be repeated, and we can go in both directions, keep drawing our asymptotes and then drawing our tangent function between all those asymptotes. So our next example is the function f of x equals negative cotangent of x plus 1. So we start with the period, which is going to be pi over b, and in this case b is 1, so we're just going to get pi as our period. And because our period hasn't changed, the location of our asymptotes doesn't change either. So those are going to be at x equals k pi. So they're going to be at multiples of pi. So if we first draw our asymptotes, we have 1 at pi and 2 pi. I can also draw one at negative pi All right, so then our cotangent function. So, oh, and it's 0. Because we have the negative in front, typically the cotangent function starts at the top and moves down. But because we have the negative, it's actually going to start down and then move up. And then the +1 changes the location of where our x-intercept would normally fall. So instead of being at 0, it's going to move up to 1. And that's going to be halfway between 0 and pi, because normally our x-intercepts are at pi/2. And then I just draw the graph. Between our intercepts, between our asymptotes. And then we have the graph of negative cotangent of x plus 1. Move on to an example of the secant function. We have f of x equals secant of 1/2 x. So again, we start with the period, which we find doing the same as we would sine and cosine. So 2 pi over b. In this case, b is 1/2, so we get 2 pi over 1/2, which becomes 2 pi times 2, which becomes 4 pi. So this means that our graph is going to stretch. It's going to be a little bit wider. So then we want to find our asymptotes. So because we have doubled the normal size of our period, that's going to affect the location of our asymptotes. So instead of occurring at pi/2, they're going to start at pi, and then instead of being every multiple of pi after that, they're going to be every multiple of 2 pi after that. So our asymptotes are going to be at x equals pi, and then every multiple of 2 pi. So if we draw our asymptotes, pi, the next one would actually occur at 3 pi, which you can't see on here. Draw my other one at negative pi. And then we know that we're going to be at 0, and then we just draw the parabola between that. And then I know that down here I'm going to be at -1, and I can draw part of my graph at least, even though we can't see the whole bottom half of our graph. We can see part of it. Okay. Last example, we have f of x equals cosecant of 2x minus 1. So if we start with our period, it is going to be 2 pi over b, which b in this case is 2, so 2 pi over 2, and we get a period of pi. So that affects our asymptotes. So because our period is exactly half of the normal function for cosecant, the location of the asymptotes are going to occur, instead of at multiples of pi over 2. So every multiple of pi over 2, we can draw our asymptotes. And at negative pi over 2. Halfway between pi and 2 pi as well. All right, so the starting point for our cosecant function, because we have that -1, it means that our function has been moved down 1. So typically our function would start at 1, but instead we're going to be moving the graph down, and it's going to actually be starting at 0. And that's going to be at pi over 4, which is going to, not an exact point on here, but it's going to be roughly and then we are going to draw our curve. I'm actually missing one of the asymptotes here at 0 and one at pi. And then the bottom half of the cosecant graph, instead of it being at -1, it's going to move down 1 and it's going to be at -2. And again, it should be at 3 pi over 4, which isn't an exact point on here, but it's a little bit past 2 pi over 3. And we'd have the bottom half of our graph. And this repeats for every period, between every asymptote, I should say. And we get our cosecant.